Let me show you how to be a good Bayesian.
Today, we are heading straight into the heart of high energy density physics. The place where lasers crush matter, astrophysics meets the lab, and Bayesian inference becomes indispensable. My guest is Ethan Smith, a PhD candidate at the University of Rochester, working at the intersection of plasma spectroscopy, diagnostics, technology, and Bayesian data analytics. Ethan studies what happens when you use some of the world's most powerful lasers to squeeze matter to extreme conditions, the same conditions you would find inside planets, stars, or supernovae. This is an episode for anyone who loves physics, who loves Bayesian methods, or who just wants to hear how scientific discovery actually happens behind the scenes. This is Learning Bayesian Statistics, episode 146, recorded October 7, 2025.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PIMC Labs can help bring them to life. Check us out at pimc-labs.com.
Ethan Smith, welcome to Learning Bayesian Statistics.
Thank you for having me. Thrilled to be here.
Yeah, it's great to have you here. Thanks a lot to JJ Ruby for putting us in contact. I hear you guys are doing some fun stuff at Rochester, doing some physics things. We'll definitely talk about that. First, both your first and last name are very challenging for me to say with an English accent as a French man, because I want to say Ethan Smith. And so it's very hard for me to say Ethan Smith. It's like twice, 2 TH in a row. That's like, you're making my life hard, Ethan.
I apologize for that. Yeah, that's my bad.
I do love the name Ethan. That sounds really good in English. In French, I don't like it's Ethan, but Ethan sounds really like very classy. You know.
Mm-hmm. Yes, I agree. Unfortunately, it's a very common name. There is another Ethan Smith in my field, and we go to a lot of the same conferences, and it causes a lot of issues.
Yeah. I am not surprised. I will confess that while I was preparing for the episode, looking you up on the internet was not easy because there was a lot of Ethan Smithies. And if you input Ethan Smith Rochester, there is actually one Ethan Smith who unfortunately died in a plane crash.
Yeah, from Rochester, Minnesota.
Yeah, exactly. But
yeah, I know him.
Oh, damn. Yeah. I was reading up on that. I was like, damn, this is a very sad story.
Not me, though. Different Ethan.
No,
I'm still alive.
Yeah, thankfully. So yeah, like actually, let's say talking about you. Let's start talking about you. So always what I start asking to the guests is, I think you know because you listen to the show, you told me in, so thank you so much for that.
Long time listener.
I'm very, very grateful for that. And so I know you do a lot of cool stuff, but listeners don't know yet. So yeah, just give us the origin story. What are you doing nowadays, and how did you end up working on that?
Yeah, so I'm finishing up my PhD at the University of Rochester. Specifically, I'm in the field of high energy density physics, which is sort of a niche subfield in physics where we use, extremely high powered lasers to compress matter to some, extremely distressing conditions. And it turns out when you compress matter with lasers, you can, recreate some of the states that you would find, for example, at the center of giant planets, or even in some cases at the center of stars. And so that lets you recreate these systems in the laboratory and directly study how they behave, sort of at a much smaller scale than you can with observational astronomy. And so that lets you learn a lot about the material properties of these, astrophysical objects. And it also lets you create some just really interesting states of matter that you can't, find anywhere else on Earth or even sometimes in the universe. And so, we create these very hot, dense states of matter for, a billionth of a second. And what the focus of my work is on is understanding how do you make a measurement, how do you make a measurement of a system that is, that extreme and exists for a very short amount of time? And two, how do you interpret those measurements? So measurements that we get out of these systems are often very integrated. There's this inverse problem of trying to take up, you have an image of this plasma that you've created, and you have to try and back out what was the temperature and density of this, miniature sun we've created in the laboratory. And so that's sort of the thrust of my PhD, is trying to use data science techniques, including, of course, Bayesian inference, to take this set of information-rich but complicated measurements and understand what's happening in these experiments. And so we've learned a lot. JJ Ruby, who was on the show before, was sort of got the ball rolling with thinking about using Bayesian inference in this context. And I've sort of inherited a lot of his work and carried it on to the next generation of grad student. And then I'm sure some grad student will come after me and carry it even further, hopefully. I didn't answer the second part of your question, which is how did I end up doing this? Which is a fair question, because it's very, when I tell people what I do, they're like, how did you even know that you could do that? And so I grew up in Rochester, New York, not Minnesota. And at the University of Rochester, we have two of the largest lasers in the world. They're actually the largest lasers at any academic facility anywhere. And those are the Omega 60 and Omega EP lasers. They're very impressive. If you ever are in town and you want to come, take a tour, each of these lasers is about the size of a football field. And we take these massive lasers and focus them down onto a tiny point, and it's very impressive. And so I went to school in the area. I went and toured these facilities as part of my undergraduate research program. And so I was like, oh, that's really cool. I didn't really think anything of it. Like, of course, this giant laser would be in Rochester. Yeah, like that makes sense. And then I was, I decided to apply to grad school. And I was, considering the University of Rochester, but I didn't want to really stay. I wanted to go, go somewhere else. But then I met Rip Collins, who is my current advisor, at a conference in Fort Lauderdale, of all places. And he told me about the cool science that they were doing with those lasers, all of the high energy density physics, the planetary science that you can do with these things. And that really, sort of convinced me that, oh yeah, like this is, this is even cooler than you might suspect by the fact that there's these football field size lasers. You can actually do really interesting science with these. And that sort of inspired me to go down that road. And then, ended up working with him for the past 5 years now. So it's been an experience. It's been a wild ride, doing a lot of laser experiments.
Yeah. Okay. So you were attracted by the big shiny laser. Basically, this was an important role.
I'll say the lasers themselves are impressive, but I didn't have any interest in using them because I wasn't, super motivated by the main mission of the laboratory for laser energetics, which is where these football field sized lasers are, is the pursuit of fusion energy, which is great and I think a worthwhile endeavor, but it didn't move me. Because it's just about effectively, making as many neutrons as you can from fusion. and you just want that number to go up, and that to me always felt like more of an engineering problem than a physics problem. And so when you go and tour these facilities, a lot of emphasis is placed on this fusion arm of the program. And so what really inspired me was the physics of it all, right? Like, to make the number of neutrons go up, you need to really understand the physics of these very extreme systems that exist at millions or billions of atmospheres of pressure. And that's a very interesting and difficult problem from a theoretical standpoint and from an experimental standpoint and statistical analysis. And so that's what really got me interested. And then, I met JJ through that, and he got me interested in Bayesian inference, which is an even more interesting subset of an interesting problem. So I would say the Bayesian inference at the end of the day is what got me more than the giant lasers.
Okay, interesting. So thanks, JJ, first, and second. Okay, so basically the physics was here from the very beginning, right? So can you also share your path into physics, and how did you first get interested in that? What was also your undergraduate training like, and how do you think that shaped your research direction today?
Yeah, sure. So I took a pretty straightforward path. I took science classes in high school. I liked it. I came from a very liberal arts family. So my parents are both teachers. My dad taught history, and my mom's an English professor. And so, sort of teaching is the family business in my family. And so I had always assumed I would go teach, but I knew I didn't want to do English or history or any of these liberal arts things because I hated writing. And so I wanted to do, I liked science and math a lot more. And so my family was always like, well, what are you going to do with that? What are you going to, a science degree, what use is that? And so I went into undergrad. I went to SUNY Geneseo, which is about 40 minutes outside of Rochester, so very far from home for me. And I had taken physics most recently as a junior and senior in high school, and I really liked it. So I said, well, we'll stick with it. And so I majored in it, and I really liked it in college as an undergrad. The plan was to go into high school teaching. So I was going to, enroll in the education school there and then do that. But then I decided that that's not what I wanted to do. And so I started doing research, undergraduate research with a physics professor at Geneseo, Kurt Fletcher, shout out. And that's where I really learned, that I could do science and that doing science is really fun. So that was a much more hands-on research project that I did in undergrad, turning wrenches, and we were building a spectrometer for ion backscattering studies or whatever. And that's when I fell in love with science and doing science, both from a hands-on perspective and just thinking about science is a really interesting and rewarding pastime. And so then I was like, well, maybe I should do more of this. And so I applied to grad school, got in, and then I've been doing it for 5.5 years now, and probably going to do more of it after this. So I think that's sort of the timeline for me. It's always just been like, well, there's probably more science to know, more physics to do. And so it's been a rewarding process so far.
Yeah.
We'll see if we run out.
Yeah. Yeah. That makes total sense. And I can vouch for your passion for the topic. So I'm also gonna bet that you're gonna do that for a long time. And so actually what you already talked about is that your research lies at the intersection of high energy density physics, plasma spectroscopy, and Bayesian inference. So could you give us a big picture of what that looks like, of what your current portfolio project is? Because I'm guessing that a lot of listeners are not familiar with high energy density physics and plasma spectroscopy.
That's very fair. high energy density physics is an interesting one because it exists at the intersection of a lot of fields, right? Because you have these very hot, dense balls of plasma. So you have, plasma science going on. You have laser science because you're using these giant lasers. You have to know how to use those and how to compress things effectively. And then, of course, how do you make a measurement? Well, these things get really hot. They emit X-rays. They emit neutrons from fusion reactions. And so you have to understand nuclear physics. You have to understand atomic physics and all these things. And so sort of at a high level, the kind of high energy density physics experiments I work on are spherical implosions. So you can think of the standard high energy density physics experiment is you take a planar foil piece of material, metal, and you just whack it on one side with a laser, drive a shock wave through it, and compress it that way. And that lets you get up to, millions of atmospheres of pressure, which is, unreasonable conditions. And it turns out that there's sort of a limit to how hard you can hit something with a laser before you just start, dumping all this energy into nonlinear instabilities and whatnot. And so a way to get to higher pressure is to do it in convergent geometry, which essentially means you take your, laser illumination from one side and you illuminate a spherical target from all sides. And so now, instead of getting compression in one dimension, you're getting compressions in all 3 dimensions, right? And so that lets you, exponentially amplify the pressures you can reach up to, billions of atmospheres, hundreds of billions of atmospheres even. And so those convergent systems are even harder to measure. At least in a planar geometry, you can, measure something from the backside of your target and maybe get a direct measurement of how fast it's going. But in these experiments, it's complete, all your measurements are completely integrated. The X-rays that you measure from these have to travel through the target itself. So you have to already know what temperature and density the target's at to understand those X-rays. And so the sort of main focus of my research is understanding what's happening in that 10 million degree ball of fire. It's a spherical plasma that's emitting X-rays and neutrons and all this stuff. How do you understand? How do you image it? How do you understand the spectra that come out of it, right? If you have bound electrons in there, they're emitting, the characteristic emission like you see, I guess, in science class when you look at the neon lights, for example, the fluorescent lights. But how do those lines change when you're compressed to 10 billion atmospheres of pressure and you're at 10 million degrees Kelvin? Like the atomic physics of that are challenging, but you can measure those transitions and you can learn a lot about the system from that. And so then the question is, how do you measure these systems? What do you measure? And then what measurements give you the most information? And so that's where the sort of Bayesian inference comes in, and working in an information content sort of paradigm where you take all these measurements, you take X-ray pictures, you take spectrographs of these systems. What information can you get, and what's the sort of max? There's a certain number of measurements you can make, right? You're limited by space on the target chamber. And so understanding the information content of each measurement and what's the most effective combination is something that is very non-trivial and something that that I'm looking into actively. And then the third piece of it is sort of what discoveries can we make with these tools, right? We have these Bayesian statistics, we have all of these images and spectroscopy. What physics discoveries can we make, and what can we do? How does that translate to our understanding of astrophysical systems and the universe at large? And I think that's really the most interesting part, is we build all these really complicated tools to all these fancy statistics and whatnot to sort of peer inside these extreme systems and understand really what's going on, not only in these systems, but in other extreme astrophysical systems. And so there's a lot of interesting discoveries that are coming out of that about atomic physics, about nuclear physics, about what role does radiation play, right? You're producing an enormous amount of photons just because you have this hot, dense ball of gas, And those, you can produce enough photons to affect the dynamics of the system. The radiation flux is so large that the system behaves differently. And understanding that is very non-trivial, because a lot of these, systems can't be created anywhere else except, here in the lab, and understanding that is very difficult. So all of this requires some level of, statistical inference, and that's really what the big picture of my work is, building the tools to do that statistical inference. Because you can make the analog very similar type of experiment is in particle physics at particle colliders. You have very distressing conditions there as well, although those are at order of magnitude higher energy than we can produce with our laser systems. But to understand what comes out of those violent particle collisions where you're at GeV, TeV energies requires very complex statistical tools, very high level understanding of your detector, and very good models of those physical systems. And they're sort of the particle physics field is a lot further along down this road than we are, and so we have to we're starting from a much lower level, and so we have to understand from a fundamental level the physics of the system, the detector, and how to do that inference rigorously.
Yeah, it's just fascinating. And so concretely, what does that look like? To work with that kind of data. Like first, what do your data look like? Where do they come from? What's the size of them? How does it look like to concretely work on these kind of projects before we dive a bit more into the modeling complexities?
Yeah, sure. So that's a good question. The data oftentimes looks like a dot on a camera, like a little spherical blob, or maybe if you're lucky, a series of spherical blobs that correspond to different times. Or if you're even luckier, you could get maybe a streaked continuous record in time with one of these streak cameras that we've developed in the field. And what it looks like is trying to build a sort of generative model of these blobs. So using our best available knowledge of the physics, right? We think we understand hydrodynamics. We think maybe we understand how X-rays are produced in plasmas and how they propagate. That may or may not be true, but we can take our best available models and try and build a generative model of how we think the physics will evolve and how that will manifest in the observed emission. And then we need to also understand how our detector is constructing that blob. And so that requires knowing what the resolution is and the sensitivity to different energies of X-rays, and as well as the statistics, right? And that's the most complicated part, and something that we're really working on is understanding, if you have a given X-ray flux, what distribution of signals are you going to measure? And, you have Poisson counting statistics for how many photons are absorbed, but then the rest of it is a complete mess because it's so complicated, and you're trying to make a measurement in a fraction of a billionth of a second. And so all hell breaks loose, basically, and the statistics get very complicated. There's correlations between neighboring data points. And so understanding that is a really sort of nuanced and complicated piece of it. But all of it is just to produce this little, dot on your camera, basically, which has an intensity, it's got a radius, maybe it's got some shape, but it's very simple data. We're using technology from the 1800s. It's like pinhole cameras and geometric optics. It's not nearly as fancy as some of the diagnostics that are being fielded in other fields, but that's largely because it can't be, right? It's very hard to have X-ray optics in a compact space because X-rays don't really refract the way that visible light does.
Damn, yeah. This is fascinating. And so maybe first, can you walk us through the main technical or methodological obstacles you face just even before starting to analyze and model these data? Like, what's the first step in your workflow when you're working on one of the concrete projects you've named at
Sure.
the beginning of the show?
Sure. So the first step is designing these large scale experiments to be done on these football field size lasers. And so that work usually starts about a little more than a year out. You propose an experiment, it gets, accepted or rejected or iterated on by the committee. You get time on the laser, you get usually 1 day. And so then your day is scheduled for the next fiscal year, and you have to design your experiment. So you got to say, all right, what's my target going to look like? What's the laser pulse going to look like? How much energy do I want? What am I looking to actually observe here? And what measurement is going to give me the most information? And so that requires a lot of simulations. So we run these very advanced, state-of-the-art radiation hydrodynamics codes to sort of predict how the system is going to behave. It's never right because these systems are really complicated, and so the codes can never quite capture what's going to happen, but we can get an idea. And then a piece I've really been pushing is trying to do it predictively. So sort of as a byproduct of this whole Bayesian inference generative modeling, you have to have a full forward model of your detector. So that lets you then input your hydrodynamic simulation, for example, and predict what exact signal am I going to observe. Is it, am I going to saturate my camera? Am I going to be able to resolve the signature, the spectral signature that I want? And so it, involves iterating, at that level to try and simulate your data and say, this is what I'm going to see. This is what I think I'm going to see. And then you do the experiment. It's completely different. And you're like, well, that's not what I thought was going to happen. And then you have to start trying to interpret that data, figure out what's wrong, what the simulation got wrong, and then try and build a better model that's able to capture the data and sort of model from physical principles, build a physical model of the system to model this data and interpret it and try and extract the most information out. So the technical challenge of designing the experiment is in its own right, a challenge because doing large scale science is challenging. It requires coordinating with a large team of people and doing a lot of very tedious paperwork to make sure that you can field the experiment you want to field. And then after that, the data is incredibly complicated. I think, JJ famously only ever published data from one shot from his entire graduate career, because these experiments are very difficult to do, and then even more difficult to analyze. And so it's considered a very, very successful PhD thesis if you can, analyze at least one data set. And so being able to extend that and do it for multiple data sets is something that's, even more challenging, even once you've built up the tools, because each individual shot of the laser is slightly different, right? And the nuance of that is something that is, because anything can happen. You can always have some fluke occurrence. There's sort of an old apocryphal tale that someone had an experiment on the laser, and a squirrel chewed through a cable on the roof, and the whole thing just shut off. And for that was it. They didn't get any data because the squirrel chewed through a cable on the roof. It's like, well, couldn't have predicted that. The code did not contain the necessary squirrel physics to predict that outcome. And so any number of things can go wrong. But being able to build a robust model and statistical inference engine to interpret these data sets and get meaningful information out I would say that's the largest sort of technical challenge. And two, these are, there's a lot of data, but it's also not a lot of data by modern standards, right? We can shoot the laser maybe 12 times in a single day, which is a lot for a laser that size. But you maybe get 8 shots of usable data. And so it's very hard to scan through parameter space and answer the questions that you might want to answer. So this a very complicated and difficult paradigm to operate in, but it's very fun and rewarding as well.
Yeah, yeah, I can guess. And how does what's the timeline, on these projects you're working on? Like, for how long does it tend to, like, what's the range of duration you guys are working on these projects? Because
Yeah.
it sounds so daunting that, like, I'm guessing you need a lot of time.
Yeah, well, I mean, the timeline for an experiment, as you know, as I said, a little over a year, but then to actually analyze that, I mean, we're talking the length of a PhD thesis, right? JJ analyzed one shot in his thesis. I'm going to analyze slightly more than one shot, but not by much. It takes, yeah, I would say it takes about 5 years to finish one of these projects. And a lot of that is because, I'm a graduate student, I'm learning. There's a lot I didn't know when I started, that I know that I don't know now. And so that definitely makes it hard to get going at the beginning. But when you're starting from scratch, right, you don't, you know, have any of the, tools necessarily built out yet. It's very difficult to get going. And so, that's sort of hopefully I've built up enough tools that my successor, whoever they may be, will be able to build on that, just as I built on what JJ did, and he built on what came before him. And so, hopefully it accelerates, but it is very challenging to be able to
Yeah,
build out
yeah. Hmm.
these tools.
Yeah. Plus, like, I'm guessing a lot of people are working in these projects, right? Physics projects are usually very collaborative. So how does that look like for you? How many people are working with you on these projects? Maybe it's even inter-country collaborations. I think it's very interesting to also look a bit at that and how it looks backstage, because not a lot of projects are as large scale and international as physics projects.
Yeah, that's a good point. So one thing that's kind of unusual about the field of high energy density physics is it is very collaborative. We collaborate all over the world. We have there's laser systems that we go use all around the world, in Europe, Japan, all over. And so there is that collaboration, but at the same time, it's small enough scale that you sort of own your project, right? So I proposed my experiments. I had a lot of help fielding that experiment, right, from a diagnostic and laser side, right? I don't know anything about laser systems, so there's a whole team of laser professionals at the lab who run the laser. And so, there's a lot of help from them. But at the end of the day, I designed it as a graduate student. I designed the target, what the laser is going to look like, what diagnostics we're going to field, and then I'm in charge of analyzing it. And so it's very collaborative in the sense that everyone works together to get good data, but you do own your own project at the end of the day. And there's a lot of freedom that comes with it to pursue what questions you think are interesting, and sort of push the boundaries. But of course, there's always you can always go talk to experts in the field, because there is that collaboration, those connections. But it's definitely not a collaboration in the sense that like CERN or Atlas are, where you
Mm.
have
Mhm.
100 people working towards the same uh, goal. It's a lot more individualized.
Mhm. Yeah, okay, I see. And so is there a particular mentor that has actually been very important for you so far in your career, or that has, helped you jumpstart your learning, or maybe unblock you on a project?
Yeah, well, I'll definitely shout out JJ Ruby here. He taught me everything I know about Bayesian inference. Um, but then, he went off to go work at Lawrence Livermore, and now he's at the Houston Astros. But we still talk. So he's been a huge help in helping me, because he was in my shoes not long ago. So he has a lot of wise advice. But then, um, yeah, it's a lot of community among the graduate students at the lab. And so there's a lot of peer-to-peer mentoring. I'll shout out David Bishel and Alex Chin. Were two senior graduate students who sort of helped me out when I first came in and knew absolutely nothing, and they sort of taught me what they knew. And now I'm the senior graduate student, and so I'm trying to pay that forward and teach me what I learned and what they taught me, and so there's this sort of sense of community among graduate students because we're all sort of in the same boat. Grad school is hard, and so it's very helpful to have that. You have someone you can talk to who's been through that. So it's not just one mentor; it's a whole lab of them.
Yeah, yeah, I can guess that. And yeah, of course, I will put also JJ's appearance on the show in the show notes.
Yeah.
For people who want to dig deeper, because JJ definitely has a very interesting background and path that I think is going to be very valuable for listeners to listen to, especially if they are interested in either physics or baseball analytics or both. Definitely give a listen to this episode. And now let's talk a bit more concretely. How do you incorporate Bayesian inference in your work, like especially so the kind of high energy density physics data you have? What advantages or limitations arise from using Bayesian techniques in your work?
Yeah, great question, and one that people ask me all the time. They're like, "Well, what's the point? Who cares about Bayesian inference? Why are you doing this?" To which I say, Bayesian inference is really the tool that you need to answer a problem like this. So at a very high level, right? You observe this data, and you need to understand the system that created it. And so this is it's an inverse problem. And so it's very difficult to just invert the data. You have to do it in a generative framework. And so right away, Bayesian inference is very well suited for that kind of thing. You don't have to do Bayesian inference. You can do forward modeling without Bayesian statistics. But it's just such a natural framework for it. And then on top of that, it allows you, what I think is probably the most powerful thing, is to include prior information in a way that you can't. So we have historical data, for example, going back several decades to the older version. The Omega laser system's been around since the 90s. So we have a wealth of historical data that helps us understand these systems. And so that you can use that as a form of prior knowledge to sort of inform, your expectations of what's going to come out of what you're going to learn from these experiments. And so that, provides a self-consistent way to sort of include that prior knowledge that will, improve the statistical inference that you're able to make from these. Because you can take a lot of measurements, but they're not, they may not have as much information as you need them to have. And so being able to impose prior knowledge is also very valuable. And then also, one thing we struggle with in our field is propagation of uncertainties, because you have very highly nonlinear systems, and sometimes you can't build a model that's able to, sort of characterize your level of uncertainty, and Bayesian inference folds that in completely self-consistently, correlations and whatnot, if you're doing Markov chain Monte Carlo. And even if you're doing something like stochastic variational inference, you can still get a much better understanding of the uncertainty in your system based on your data, which is very non-trivial for these systems. So I would say that's the big three reasons why we use Bayesian inference to analyze the data. It's because I think it just makes sense.
Yeah, I mean, preaching to the choir, but yeah, completely relate, of course. And actually, can you describe one experiment or project that you're particularly proud of, where you used Bayesian inference, what you measured, why it's significant, and what does the model look like?
Yeah, sure. Well, it's still ongoing, so it's not done. I don't know if I'm allowed to be proud of it if if it hasn't been published yet, but that's fine. So one thing that the sort of the what's become my main project at this point is making a sort of measurement of the equation of state of a billion atmosphere pressure plasma. So the equation of state is, just the relationship between pressure, temperature, and density, basically. You think of the ideal gas law, van der Waals equation of state, maybe, to name a few. And so it's a very important material property, right? Because it says if you're at a temperature and density, what's the pressure, what's the energy density, and so forth. And so we've sort of developed the tools to do this at lower pressures fairly routinely. You can measure the temperature, density, and pressure of a planar experiment, for example. So you can get all the very high pressure, but you can't, as I said, there's a limit to how hard you can hit something with a laser. So you can't measure the equation of state beyond, 10 million atmospheres or so. And so, you have to go to a convergent geometry, but that's very difficult. And so sort of what's become my mission is making that measurement using Bayesian inference techniques and other statistical methods, machine learning and whatnot, to take this big data set that, consists of multiple different X-ray cameras, spectrometers, all sorts of, the full kitchen sink, and analyzing that data set, this multi-messenger data set, comprehensively at the same time, and sort of in the data space as much as possible. So sort of from first principles, if you will. And so this was a really complicated system just to build, right? You have to build models of all these detectors and understand the statistics in some sense, and then do the inference, which is going to be a very high dimensional problem. Requiring the very advanced sampling tools provided by PyMC and other libraries. And so what we were able to do is take that data set and throw this very complicated model at it, it's complicated, but it's simple, right? Because it's basically, you have your temperature and you have your density and your pressure, and you have a very simple but sort of complete physical picture of how they evolve in time and space. That's sort of parameterized in terms of these physical quantities, but flexible enough to be able to fit the data while encoding, our prior belief on the physics of the system. Like, for example, we think the temperature should go up and then down, right? And stuff like that. And so doing that, building this model that, treats the evolution of the system and then, propagates that forward. What X-rays does that produce? How do we observe those? What would we measure if that were the case? Bayesian inference, the likelihood of data given theta. And then we are able to sort of independently constrain the pressure, temperature, and density from the available suite of measurements. And so that gives you sort of separate measurements of what's the temperature and density and what's the pressure. And those are related by the equation of state. And so this gives you a very fancy way to measure the equation of state using these advanced statistical methods. And so we were able to do that for the first time, and that gives you sort of insight into what physics is happening, right? You can compare it to your models. You can do further inference on those conditions that you infer, and try and understand what's happening here. Is there sort of interactions that we aren't taking into account in the physics of the system? Is it just the ideal gas law? Is there something else going on? Are the photons that we're creating, producing their own pressure? It lets you ask a lot of interesting questions, and it's to my knowledge, it's the first measurement out there at these billion atmosphere pressures. And so, we're still working on putting that together for publication, but just the sheer lift of putting it together and doing it in a self-consistent way is something that I'm proud of, and has really pushed what JJ did with his single diagnostic single shot analysis to a more complete framework. And then because I took multiple shots of data, I think I've analyzed seven shots now. So that's a vast improvement for the statistics. Square root of n was so much more certain now.
Yeah. Damn, well done. Yeah, I know this is such a hard work, but very impressive. And so first practical question, because I'm always curious, what did you use to code the actual model, and to sample? Like, did you use any already existing package? Did you have to come up with your custom packages, maybe even custom sampler? How does it work? What does it look like?
So I am a big proponent of Python, doing everything in Python, which is an increasingly popular opinion, turns out. Python, when I first started, no one in my lab was using Python, which was crazy, except for JJ. It was everyone was using like MATLAB, Excel, Mathematica. Python was
Excel. Damn, this is
a lot of people still use Excel. I will
Wow.
say, in their defense, what they're able to do with Excel is nothing short of magic. I mean,
Yeah. I mean, at that level, you have to be an Excel.
they're doing
magician.
everything I can do in Python. They are doing in Excel. It just looks ridiculous.
Yeah. Damn. Wow. Okay. But good choice. I completely support you, Ethan and JJ in this endeavor. So go on.
So we're big proponents of Python, and the sort of big knock on Python is that it's slow. But that's actually becoming less and less of an issue when you have things like just-in-time compilation with JAX, and other things that are automatic differentiation. All of that is sort of closing the gap between Python and these sort of machine level, Fortran and C++ and whatnot. And so the ease of use is so much better that coding in Python is really, I mean, you obviously agree, is the practical choice at this stage. And so, a lot of it is pre-existing, right? There's the JAX libraries. A lot of code exists. I didn't have to recode, np.traps or anything like that. But, there's a lot of very bespoke code that I had to rewrite in JAX. That's, an implementation that doesn't exist, that does exactly what I wanted to do. And so I, had to do, is a lot of software development, considering I came into college or graduate school rather with basically zero Python experience. And so I had to teach myself from the ground up how to code in Python, and then how to code, in JAX, and then how to develop a large scale software package. It's not beautiful, but it does work. And that's another thing that I guess I should add that I'm proud of is, the sheer amount of code that I've written for this project. It's a massive repository, just to, analyze a couple pieces of data. But yeah, shout out to Python, shout out to JAX. We used to use PyMC as our sampling library to do the inference. We switched recently to NumPyro because that was, this is when, NumPyro was sort of new and JAX was sort of cutting edge. And now I think PyMC uses JAX at its back end.
Yeah, I mean,
And so-
you can. Like we have the three backends. So C is the default one. You can use NumPy and you can use JAX. So yeah, depending on the project you're working on, can be useful to use NumPy, or it will be faster using JAX. It depends on your model. So yeah, that's great. So yeah, but anyway, you're using a very good open source package, and you build on top of it. And you're using, it seems, what are you using as a sampler? Like latest MCMC or?
So yeah, it depends. Usually we'll use, nuts, no U-turn sampler. Do it just, you have to sort of coax it to do what you want on occasion, but it's sort of the Ferrari of samplers as far as we're concerned. Occasionally it will, when you drive a Ferrari on a road full of potholes, you will occasionally encounter a negative result. And so we may have to use, something like sequential Monte Carlo SMC or some other more robust but slower nested sampling is another one that I've used a lot. So it's unfortunate because you'd like there to be one sampler that always works, but that is never the case, and you always have to do something else. And sometimes when you get really desperate, you'll be like, all right, we've got to use a different, totally different sampling library to get what we want.
Mm-hmm.
But that's part of the art of it and part of the fun.
It's already working for most of the, like for 98% of the cases, MCMC will be amazing. I mean, that's, and so, yeah.
And
So
that's a
it's great to
miracle.
hear
Yeah.
that you didn't have to code your custom sampler, right? So you see, folks, you don't need to write your custom samplers anymore. Like especially, I'm speaking to the among econometricians among us. Like, don't stop writing your own custom GIF sampler. just
Yes.
just use the ones that are in PyMC or NumPyro or Stan or whatever you're using as a probabilistic programming language. It's gonna work well. And there are now more than the net sampler. There are many more of them. So
100%
yeah,
agree.
yeah.
And I've been trying to proselytize a little bit, around at different research groups. I've got some Bayesian inference outreach presentations that I've been giving,
Nice.
trying to spread the word that hey, Bayesian inference is not as hard as it used to be. In the olden days, you don't have to write your own sampler. You can just use one of these excellent pre-made ones that are. I mean, they're only getting better and more sophisticated.
Yeah,
And so
exactly. So
the barrier
and
to entry is so much lower now.
exactly, yeah, it's way lower. So like now you can spin up a Bayesian model and sample from it very fast, and don't even have to worry about the sampling issues because it's all taken care of for you. So I would say it's a great time to leave.
hmm And a lot of people are scared of Bayesian inference because it sounds fancy, but it's really quite easy. You build your model, turn the crank, Bayes rule, and get out your posterior.
Yeah,
It's
yeah, exactly. Yeah, not a lot of things to do now. It's pretty much all automated. So
it's solved. Yeah, Bayesian inference is it's all done.
Mm-hmm. Yeah. And actually, do you have any good practices that you want to share with people when they're working with big code bases, as you are? Well, in your case, in Python, but can be anything else. Like, what are the good practices you've found to not lose yourself, basically, when working on these big code bases, and also probably to help collaboration, as we were talking about.
Yeah, well, the first thing is always comment your code. And
Yeah.
I say this with full knowledge that I am not very good at this, but always, for your future self, at the very least, write down your thought process so you can come back to it. But then on a sort of more sophisticated level, um, there's a sort of white paper by Andrew Gell-Mann. I think it's called A Principled Bayesian Workflow, that sort of lays out best practices for constructing a model. And so, you construct your model, you test the prior predictive distribution. You say, okay, is my prior correct? And then you go. And I think one thing that's really useful, especially in the sort of work that I do, is building a sort of synthetic experiment, and making sure that you can get out the information you think you can get out, right? Because if you build this whole synthetic set of synthetic diagnostics and your model, and then you take the data and then you try to analyze it, and you actually don't get any information out, well, great. You wasted a bunch of time and money on that experiment, and you didn't get what you wanted out. And so being able to sort of, before you've even done the experiment, predict what you're going to measure, and then what information you can get out of that is hugely helpful, and really should be a prerequisite for doing any of these experiments, is showing that you think it's going to work. I mean, there's value in just shooting a laser and seeing what happens, but at this stage, the field is advanced enough that we should be doing this a little more predictively. And then to sort of benchmarking and testing your model along the way. And so one thing that I really struggled with is I sort of put the model together all at once, and then I just pressed go and it didn't work. And I was like, well, why didn't it work? What's breaking? And so then I was like, well, okay, I took it apart, and piece by piece, and I tested each module, made sure it did what I thought it was doing, ran the inference, ran the synthetic experiment. But let's say there's no noise, it's a perfect measurement. Does this work? And so building confidence in your model is very important, and convincing yourself that it works so that you can convince others. And that helps you find a lot of the issues, because you definitely can lose yourself in in the model building process. As fun as it is, once the model gets too big, there's nothing you can do. You gotta just one brick at a time, and after you place each brick, make sure that brick is a brick.
Hmm. Yeah. Yeah. Okay. Yeah, I see what you mean. So basically, having a principled patient workflow, building block by block, and testing it along the way. Is that correct? So how do you benchmark and test your model, actually? What does a good model look like to you in this kind of project? How do you call a model good? How do you evaluate it? How do you benchmark it? I think it's a very important question, not only in your case, but in everybody's case. Like all my models, I need to benchmark them. So yeah, I'm curious, what does that look like for you, and what does that mean to have a good model?
Right. So for me, for the specific use case that I work on, well, all models are wrong, but some models are useful. So a good model is one that is useful, that you can use to get useful information about your system out. And so what that usually looks like is we'll run a state-of-the-art full physics simulation, hydrodynamics code, simulate our experiment, generate synthetic data from that using our state-of-the-art detector models, and then do inference on that synthetic data and say, okay, so we know what the ground truth value is from our simulation. Can we recover that with our model? And oftentimes the model is a vastly simplified physical model, right? Because these state-of-the-art simulations take hours to sometimes days to run one simulation. So you can't really, iterate over parameter space on that time scale. And so it's important to do this full physics and benchmark your, reduced order model on that. And then, if that works, great. So maybe you benchmarked it against a 1D simulation. It worked, great. You go up to a 2D simulation or a 3D simulation and see, does it still work? Do we still get useful information? And so verifying that, you can get out of this set of integrated measurements, can you recover the ground truth value when you in the limiting case, when you know what it is? And that builds confidence that, the result you get out of the experimental data is meaningful and useful. And so that's a very important piece of model development for the specific use case I work on. I don't know what that really looks like in other fields where maybe in social sciences and whatnot. I don't know if you can simulate an entire economy and the stock market. Maybe you can, but
Yeah, you probably can. I think Jesse Grabowski would be able to talk about that, but I know he does a lot of simulation work. I mean, at some point also it looks a lot like physics simulations when you're simulating a full economy.
Yeah,
there's a lot of interactions and dynamics, and so state space models actually look a lot like physics simulations. You can definitely use that in physics. I'm sure.
And a lot of physicists do go work on Wall Street after they're done with their PhDs. Yeah, it's either baseball or Wall Street. That's the
right. Yeah. I mean, you can really do anything with physics. So, that's what you could have answered your parents. Well, you can do anything with a physics degree.
Well, I didn't know that at the time, but I know.
Yeah. Yeah, now you can. And actually, since you talk about simulations, I know Andrew Gelman, for instance, is a big proponent of simulating the data and testing the models on simulated data, which I do all the time also because, I'm a good student. I listen to Andrew. He knows way better than I do. How does that look like for you? How do you balance simulation, modeling, experimenting your own work? And a bit more generally, which side, if there is one, theory or experiment, do you find more challenging or more rewarding?
Yeah, well, so I do a fair amount of simulations, right? I use these large-scale physics codes to simulate my experiments. And as I alluded to earlier, they're sort of always wrong. They're not predictive, which is a big problem, especially when you start thinking about using implosion experiments for fusion applications, right? You want to make more neutrons, and so you want to be able to, use your simulations to say, well, what do I change to make more yield, more fusions? And so having a code that's not predictive is not particularly useful in that capacity. And so for me, the use of the simulations is that it provides, a sort of physically self-consistent system to test your models on. It's not correct, it's not a perfect picture of what's going to happen in your experiment, but it provides a sort of, synthetic universe, a self-consistent universe for you to sort of test your models on. And so, to me, I think any experimentalist would tell you that the experiment is king. What actually happens is the most important thing. And, the theory should try to be predictive of what actually happens rather than, oftentimes what happens is you'll do the experiment, it doesn't match your initial simulation. And so you'll tune your simulation to sort of match it, and you'll add some fudge factors, whatever. And it's like, oh, look, we discovered this thing. It's like, well, it would have been nice if you could have predicted it beforehand. And so I sort of, make fun of my theorist colleagues a little bit because, they have these predictions and it's like, well, does it match the experiment? If not, then I don't, but then they'll always fight back. Well, maybe your experiment is wrong. It's like, but it happens. Like this, we're all sharing the same experiential reality. We all agree that we did the experiment and this is what happened. But it's an interesting interplay, because both sides are saying the other one is wrong, and that it has to be, we have quantum accurate density functional theory calculation. This is the truth. But every side has its their skeletons in everyone's closet. Things that we don't understand. And so I'm trying to sort of unify those two silos is an ongoing struggle, and something that we've been trying to work on, sort of have theorists and experimentalists work together on experimental design, for example, to do an experiment that better answers the outstanding questions. But as insofar as I go, my philosophy is always that the theory should try to be predictive of the experiment, and if it's not, then it's not a useful simulation outside of this idea of a synthetic experiment to benchmark your models.
Yeah, that makes sense. And yeah, completely agree with you with your way of viewing things, for sure. That's also in my own work how I do it in the end. Experiment and out-of-sample predictions are king, right? It's like if they don't go well, but the rest is looking good, then my belief in the model being an accurate depiction of reality is definitely decreased by a lot. And something I am very curious about, just to change gears a bit more general question, but it seems to me like high energy density physics can be contributing to a lot of different subfields of physics. Astrophysics, planetary science, materials research, even under extreme conditions. How do you see high energy density physics? It's hard for me. Contributing.
Well,
to
we
these
usually just
subfields.
abbreviate it as HED physics, if that's easier.
Okay, HED. That's gonna be easier. Yeah. So how do you see HED contributing to the different subfields, and what are maybe some exciting projects that are looking into that currently?
Yeah, absolutely. So, I sort of alluded to this earlier, but you're recreating states that exist at the center of astrophysical objects. And so it turns astronomy from an observational science to one that you can do in the laboratory. And so one of this is sort of the focus of the Center for Matter and Atomic Pressures, which is an NSF Frontier Center at the University of Rochester. So we're, using NSF money to get time on these lasers to study outstanding sort of astrophysical questions. And sort of one of those questions is sort of dealing with the miscibility of hydrogen and helium in these gas giant planets. So, we know now from the Juno missions and other, space probes that we don't really understand what's going on inside these gas giants, inside Jupiter in particular. Is the core, is it a solid core? Is it dilute? Turns out it's somewhere in the middle, where it's the sort of fuzzy core. And that sort of flies in the face of everything we thought we knew about planetary formation. And so, these laser-driven laboratory experiments are sort of, positioned to help us understand things about how how the component pieces of the center of Jupiter, how do they behave under those immense pressures, right? You have, millions and millions of atmospheres pressures at the center of Jupiter. And so how does hydrogen behave? It turns into a liquid metal. I mean, that's weird. We should know more about that. And so being able to create that state of matter in the laboratory and study how it behaves has huge implications for our understanding of these gas giants and other even terrestrial planets, right? Even our own Earth, right? There's a lot of really interesting geoscience being done at these laser facilities through CMAP and otherwise. And so that's one end. And then, you can go to these convergent systems like I have that are, can create stellar interior relevant conditions. And so you can start to understand, our own sun, which there are still a lot of questions about, turns out, even though it's the closest star and we can make a lot of measurements of it. You can't really see, you can't send a probe into the center of the sun. Turns out it'll get incinerated. And so we don't, know even there's some debate about what's in the sun. We're not 100% sure, what the metallicity, what elements are in the sun. And that, stems largely from disagreement between spectroscopic measurements and helioseismological measurements. So that's, measuring the oscillations of the sun and inferring from that the composition. And so, those are sort of two separate measurements, but they both require knowledge of, high energy density plasmas and, their equation of state. How does sound waves propagate through the sun? That requires knowledge of the material properties of hydrogen plasmas at billions and billions of atmospheres. And then, spectroscopy requires knowledge of atomic physics at distressing conditions, millions of degrees. And so, being able to create these systems in the laboratory is hugely impactful for understanding the physics at play, or rather, it could be. I don't think it's living up to its potential as of yet, right? And that a large part of that is this. There's a large amount of siloing in physics in general, but especially in this field, because you have people who know how to do laser experiments, and you have people who know how to do astronomy and astrophysics. And they don't talk usually. They're in different subfields. They might meet at a conference, but they don't. They're speaking different languages effectively. And so being able to bring them together and say, hey, what are the astrophysical questions we can answer? Because we're doing these experiments based on what we can do, and that's not always directly relevant to these astrophysical. So bringing in astrophysicists and say, if you could snap your fingers and we could tell you one thing about, the matter at the center of Jupiter, what would it be? And then finding ways to answer that with laser experiments. And that's one of the missions of CMAP is I think they're calling it in-reach as opposed to outreach, talking within the scientific community and trying to, break down the walls of that silo, because it's very difficult to merge disciplines when each one is so myopically focused on what they know and what they know how to do. And then I'll just say the last thing that we're sort of doing is sort of pushing the boundaries of these fundamental theories in physics, right? When you assemble matter to these extreme conditions, you start pushing towards the breakdown of these quantum mechanics, special relativity, not general relativity yet. We can't make black holes. Everyone always asks me, so can you make a black hole with this laser? It's like, no, not even close. Sorry. But we can sure get things hot enough where special relativity begins to play a role. And so what we're able to do by pushing the boundaries of these fundamental theories is to see where they break down, right? Quantum mechanics is sort of always considered in a vacuum, zero temperature, you have an isolated atom. Well, what happens if you put that atom in a dense plasma that's 10 times the density of lead? It's very difficult to calculate, but we can do it in the laboratory and we can observe what happens. So I'll shout out work by my colleague David Bishel, who is measuring. He's a spectroscopist, and so he's using implosions and doing spectroscopy on those, and seeing how the presence of this incredibly dense plasma affects the energy levels of your atom. And it turns out that you think of the energy, the quantized energy levels of your atom as sort of fixed, right? 13.6 eV for the hydrogen. But when you're in a dense plasma, they can actually shift. You can move the energy levels of your atom, and that's kind of very complicated to understand and model. Like the free electrons are being sort of sucked inside by the nucleus and screening your energy levels so that the energy levels shift, and that's sort of changing how we think about quantum mechanics and energy levels and bound states and free electrons and all that. And so there's a lot of interesting physics to be done with these giant lasers, and we're really only just scratching the surface, largely because we couldn't really interpret these measurements too easily until now. And we live in the information age now with all these diagnostics and Bayesian inference and machine learning. So lots of interesting stuff.
Yeah, this is absolutely incredible. Thanks for sharing that on the show. Definitely add any links that you think are going to be relevant to the show notes, because I'm sure a lot of listeners are going to want to learn more about the different topics research topics you just talked about. And so you've been generous with your time, so I'm going to start playing us out. I still have a lot of questions for you, but a main one is, you see, well, you just said we're living in a great time now when it comes to diagnostics. Do you see any new diagnostic technologies, whether that's novel detectors or quantum sensors or anything else, that you're excited about or keeping an eye on, not only for your work, but for your field in general?
Yeah, well, so this is a great time for diagnostic development. We're, at the LLE, we're developing new diagnostics all the time. Many PhD theses are devoted to developing these new diagnostics. In terms of, I think the most, the one that I have my eye on is at LLE, they're developing the next generation street camera. And so a street camera, basically, it's just a detector that takes a signal, an X-ray signal, and sweeps it in time. So you get a continuous record of your X-ray. So you can use that to take a time-resolved spectrum, or, for example, a time-resolved image. And so they're very useful diagnostics, but they always break. And there's a joke going around that there's a conservation of street camera. So if one is working, that means somewhere in the world there's another street camera that is not. And that holds fairly true for me in my experience. And so they're working on the next generation that's going to be very robust. And it's Sean McPoyle is the graduate student who's developing it. And so he's doing a very thorough bottom-up approach, simulating the electron optics that are required to build this thing, and building the best possible one, optimizing it from a very from first principles approach. And so that's going to enable really precise, ultra-fast spectroscopy of these, billionth of a second lived plasmas. And that's going to be able to, totally push the boundaries of what we can measure. Because, even, Dave Bishel's work looking at these moving energy levels, that measurement is, by modern spectroscopic standpoints, terrible. Like the resolution's not super great. The time resolution's not, you can see that the lines move, but it's, you don't get much more than that. And so this next generation is going to be, much more, it's going to be higher resolution. It's going to be better contrast. And so that's something that I'm really excited about. It's called the BHX spectrometer. The other thing that I'm really excited about, let's see, we have time-resolved X-ray diffraction. So one thing that we do a lot of, X-ray diffraction, standard in materials science. We also do it at this sort of nanosecond scale where we blast a sample with a laser and then we hit it with a bunch of X-rays, and you can measure the diffraction peaks that tell you what structure it's in. And so that's told us, we've discovered new states of matter using that technique. And so but it's a single measurement. And so now we're developing the capability to do time resolved diffraction, where you're measuring the movement of those Bragg diffraction peaks with time as you compress it. So you can see phase transitions happen, which is a really outstanding question in material science in general, is how do phase transitions happen and how do they happen at extreme conditions? And so that's going to be very, watching that closely to see what insights that develops. And then, last thing is, the sort of development of high rep rate, diagnostic technologies. Because right now we're sitting on sort of a pond of data. We've been operating the Omega laser since the 90s. There's a lot of data, but we're taking 10 shots a day, 1 shot an hour, basically. And that produces a lot of data, but it's, in terms of, compared to particle physics, it's nothing. Like I could store most of the data. I could store all the data I've taken for my PhD on my laptop, and it's not an issue. But the next generation of lasers coming out are going to be much faster. They're going to be dipole or diode pumped, and then they're going to be able to fire on the Hertz scale. So we're talking like 1 shot every 5 seconds, or a minute even. And so that is going to rapidly increase the amount of data that we have just in general. And so understanding what to do with that is a challenge that I think is, sort of uniquely suited for the sort of data science techniques that I've been developing and other collaborators have been working on to understand that. And then, what can you do if you have a shot every 5 seconds? Like, what do you do with that level of repetition rate? What science questions can you answer, and then how do you process that data and deal with it? How do you even build a target that you can shoot that fast? And so there's a lot of, I think that's really the frontier of the field. It's where the field is headed, is this high rep rate frontier, to be able to start behaving, more like other fields where you do a bunch of experiments and you can get very good statistical certainty in the result.
Yeah. And actually, that reminds me, earlier in the show, you were saying that in one of your projects, the data changes with time and space.
Mm-hmm.
So I'm curious, how are you modeling that, if you already are?
Well, so I mean, it goes, at the end of the day, it goes back to the hydrodynamic equations, Navier-Stokes, and then however you want to reduce it from there. And so understanding how it evolves with time and space is a very non-trivial physics problem, especially when you're dealing with laser plasma coupling and beyond just the basic physics questions of what's the equation of state of this thing. How does now you introduce a laser field, and the transport properties are even less well understood. And so I've sort of adopted try and keep things as simple as possible. So Newton's, keep things at a Newton's second law level, right? You balance your forces, right? The laser is exerting some force on your target, and then that necessarily produces an acceleration. And so one, nice thing about Bayesian inference is you can have these parameters that, you infer from your data. So if you have a trajectory of your, imploding capsule, you can say, okay, well, I know the acceleration from these images that I've taken, right? I can see this thing, converging. So I know, that I know it's going inward. There must be some force driving that acceleration. I can infer that from Bayesian inference. And so trying to keep the models as simple as possible without, so you don't have to solve the full Navier-Stokes equation with radiative transfer and all that. So that's the level that we're at. In the future, we'd like to be able to use these state-of-the-art codes, these radiation hydrodynamic codes, as the model, right? Because that's a complete picture of all the physics involved. The problem is they're slow. They're taking hours to run one simulation, and they're also, there's a lot of parameters in these very complicated codes, as you can imagine. And so, the sort of future is to build a sort of Bayesian version of one of these codes that's, ideally written in Python, fully differentiable with respect to the parameters, and much faster. And probably that looks something like building a neural network surrogate of one of these codes or something. we'll see what the future holds, but that's the dream, is to move to a, more and more complex physical models, sort of trying to follow the blueprint that the particle physics people do, right? They have this very complicated, complete physical model, and they use that to make predictions. And so we'd like to be able to do the same, and then infer, using the best available models. But for now, it's very simple pictures.
Yeah. I mean, you have to start somewhere, especially with all the complexities you were talking about before, and the block building philosophy you were talking about, which I definitely agree with, because that way you know what is working and what is not. So it's extremely helpful. No, I was asking because I hear spatial temporal and I think about Gaussian processes, of course. So, I was curious.
Of course, yes.
Yeah.
And
you're doing
that's part of the
the
simple model, right? When you don't know how something evolves in time, right? The temperature is a great example. That's, depends on all of the thermal processes, conduction, radiative heating, expansion. All of those things go into that, and it's very difficult to model that. But the temperature goes, up and then down. And so the perfect sort of vehicle for that is, of course, modeling it as a Gaussian process. And that's, an infinitely flexible a tool for that, and something we've leaned on a lot. Yes, I forgot you're a big fan of Gaussian processes. I should have led with that.
I am. So did you try actually some GPs on that, or that actually doesn't work because one, the data is too big, or even better justification would be, well, we know more structure than we can impose on a GP?
No, yeah. Well, so we use Gaussian processes I use Gaussian processes at every available opportunity, just because they're a very powerful tool. So what we'll often do is model a piece of the model. For example, the temperature history is a function of time as a Gaussian process, right? And so that's sort of, there's stuff that we know more about, right? The Newton's second law piece I was talking earlier. There's physics pieces that we know, and when possible, we use the physics. But when you can't, you want to use something that does, is flexible and able to capture the data. While we know the temperature is a continuous function of time, and so Gaussian process is the perfect sort of prior to place on that, and sort of lets the data inform what that is while giving an estimate of the uncertainty.
Yeah. Agreed. This is a very interesting thing to do, and both in NumPyro and PyMC, you have very good GP modules that you can use flexibly in your models without forcing the model to be a pure GP. So this is something extremely helpful. Maybe a few more questions before I ask you the last two questions. I promise I won't be too long, but I'm curious now, playing this out, thinking a bit more about the future. What's your vision for scaling up experiments? In whether that's energy, repetition rate, fidelity. In the next few years, what do you hope the field will get when it comes to scaling up experiments?
Yeah, well, so it's going to be a sort of two-pronged approach. I think what we're already seeing is a move towards high rep rate at existing facilities. So the sort of most prominent example is the dipole laser at the European XFEL in Hamburg, Germany. And so they've built a rep-rated sort of Joule class laser that can do, one shot. It's supposed to be, I think, 1 hertz, but it's not quite there. It can shoot, every couple minutes or so, which is much better than the, previous version, which had like an hour cool time or whatever. And so now you can just, rattle through a bunch of different, targets, and you can do someone's whole PhD thesis in an hour. And so I think moving that direction, this high rep rate is very, that's where we're heading. And I think that's a good direction to head. The other piece is going to be, we're going to need to build new facilities. And, the Omega laser is, as I mentioned several times, very old. It's from the 90s. It's using 90s laser technology. It's showing its age. And it's a really good facility. It does really good work. But we're going to have to start thinking about the next generation of laser drivers to be able to sort of keep pushing the boundaries. And so obviously the National Ignition Facility out at Livermore is, megajoules. So it's, 10 times bigger than the Omega 60 laser, which is only, 30 kilojoules. And so that serves its own purpose, but you can only shoot that once a day because it's so massive. The lamps take forever to cool down. And then you create so many neutrons from your fusion reactions that it, makes the whole chamber radioactive. And so, there I think is a middle ground here, sort of between the kilojoule class laser that Omega is now and the megajoule laser at NIF. Probably like 100 kilojoules is probably the sweet spot, where it's also, you're able to reparate that and do all of the cool science that the Omega 60 laser does now, and more, right? Because you have a little bit more energy, but being able to do that at scale, at reparate, I think would be a very worthwhile endeavor. And we'll see they're in discussions to build the next generation of Omega 60, which is sort of tentatively named the unimaginative Omega Next, which I think is a terrible name and needs to be changed before we start proposing it to the government. But I think that's the way forward is reparate and more energy. But I don't think we need to go. People are talking about building NIF 2, right? Because now that they got ignition over there, we need to build a 10 megajoule laser, and that's great. But I think there's a lot more interesting scientific questions that can be answered with a 100 kilojoule laser, like Omega 60, but Omega Next.
Damn, yeah, that that sounds like a powerful beast to build. Now, one last question before the last question. I know, so you're maybe starting to teach, or at least you're doing some Bayesian outreach, as you were saying. So I'm curious, what advice do you give younger scientists entering the field? What skills, mindset, training do you think are most critical?
Yeah, well, I think one thing I wish people had told me, and I think a misconception about grad school in general, is I tell people I'm doing my PhD in physics, and I'm like, oh, you must be so smart, you must be a genius. And it's like, I don't think that's necessarily true. I think more than anything, it's mental toughness is what you need because grad school is a grind. And there are days when you're like, I hate this, I want to quit. And there are just as many days where like this is great. Like I feel like I'm unraveling truths of the universe, and being able to sort of manage those highs and lows takes a remarkable amount of mental toughness. And so what I've seen over the course of my career is graduate students who are successful are ones who have are able to grind it out. And it helps to have a sense of community. And so that would be my other piece of advice: is make friends with your lab mates and fellow grad students, and just it'll get better. Allegedly, it's important to have mental toughness and not lose sort of the big picture side of it all, right? Because you're doing cutting edge science, and it's very remarkable in that sense. And so being able to not lose sight of that while maintaining your toughness is I think that's the key to success. That's my advice.
Yeah. So resilience and compounding effect of small daily grind is definitely something you recommend, and I definitely push to with my own students, like, because I get the same reactions each time I talk to people about what I do, and it's always like, oh yeah, I'm not good at math, it's not for me. And I think trying to develop more of that growth mindset where it's, I'm not sure it's for me either, it's just I love it and I love learning new things, and I think working on difficult problems is the best way to learn new things, because otherwise I get bored. But this is extremely uncomfortable and hard, because by definition, if you're always at the frontier of the field you work in, you're working on things that aren't solved yet. And so you don't have that feeling of being comfortable, because you never know exactly how you're going to solve what you're working on. And so,
or even if there is a solution.
Yeah. Oh, so that's even worse. Yeah. Let's not open that Pandora's box. But yeah, no, for sure. Yeah, you don't even know if there is a solution. And so, yeah, I think loving what you're working on because it gives you something you really value, and just being able to persistently get 0.1% better every day is gonna give you a very valuable compounding effect.
100% agree.
Awesome. Well, Ethan, I think it's time to let you go, because as you've seen in the Google Doc, I have more questions, but let's call it a show. But before letting you go, of course, I'm gonna ask you the last two questions I ask every guest at the end of the show. So first one, if you had unlimited time and resources, which problem would you try to solve?
So, all right, this is a bit of a niche one. But I'm very interested in this idea of picno nuclear fusion. And so, most people are familiar with thermonuclear fusion. That's what happens in the sun, right? You have, hydrogen molecules very hot, they crash into each other and they fuse. There's another mechanism that's believed to occur in some super dense astrophysical objects, like in white dwarfs, for example, where you have sufficient density that you have, two atoms that are close enough together that they spontaneously fuse, not due to, high velocity collisions, but just because of proximity. And if it, it sounds a lot like cold fusion, but, this is a little bit more scientifically sound. And so there's, a long-standing belief of my advisor that you can do this on, a laser facility like the National Ignition Facility, but you would need to make it incredibly high density and incredibly, you'd have to keep it cold enough that thermonuclear fusion doesn't happen. And so if, the government gave me unlimited time and money, I would just devote the entire time of the National Ignition Facility to trying to make as dense of an object as I could. And, maybe we'd get the black hole that everyone always asks me about. But ideally, you'd show, this picno-nuclear fusion is, I think, one of the coolest things. And it's a largely unsolved problem because you can't, we have no idea what's happening in those white dwarfs, and we can't yet make that plasma in the laboratory. So that's the problem. It's a personal pet project.
Okay, yeah, I love that. And niche answers are definitely encouraged to that question. Second question: if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
So this is going to be controversial given the he was kind of the villain in Oppenheimer, but I'm going to go with Ed Teller, just because he's sort of a controversial figure in scientific history, but I think he had a very interesting view on science and sort of interesting mind, and I would love to sort of pick his brain. He also a lot of the work that he did, post Manhattan Project, laid the groundwork for the high energy density physics as we know it today. Right? He was using nuclear bombs instead of giant lasers as a driver. But it would be interesting to sort of pick his brain about the foundations of the field, and of course he helped invent the Metropolis Hastings algorithm that is the foundation of all of Bayesian inference. So I'd be interested to talk to him about that.
Damn, yeah, great answer. And I think you're the first one to actually answer that. So
I would not be surprised. I don't think that's a very popular answer.
Awesome. Well, Ethan, thanks again for being on the show. That was fantastic. You were able to cover so much ground. I am very happy about that. You're doing fascinating work, so I am extremely happy to have you on the show. Let's make sure to add all these great resources to the show notes. I've already added a few of them, folks, so make sure to check them out if you want to dig deeper. And Ethan, thanks again for taking the time and being on this show.
Thank you so much for having me.
And thanks again to JJ Ruby for putting us in contact.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbasedstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbasedstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbasedstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.